three Maxwell's equations. Okay, and let's continue the discussion. And in fact, let's try to finish up the discussion. Three photons, essentially. Three classical photons. Classical because we haven't quantized it, and classical because we're just solving Maxwell's equations, which has no each bars and then let me just briefly recap where we were. So we chose the Lorentz gauge. And the Lorentz gauge, the divergence, the four divergence of the vector potential is 0. And the divergence of the electromagnetic stress tensor just because it becomes the wave equation for the photon vector potential for each component. So just becomes four wave equations for nu equals to 0 to 2. And what we did was to write down A in Fourier space and decompose it into modes, polarization and Fourier modes, right? So decompose a view into Fourier modes. And sum over polarizations. Polarizations just means where the vector potential is pointed. And it looks like this. So A mu of x is equal to the integral over momentum. And the convention, actually for later on, you'll see why we do this, divided by square root of 2k, where k is the magnitude of the momentum vector. And then, then you have a sum over the polarization. But we realized that we can get rid of, so let me just say this, we impose this, we impose that, and use residual gauge symmetry, gauge freedom. Actually, let's do it in Fourier space. We were able to get rid of one mode in the decomposition by canceling the polarization that is parallel to K mu. Okay? So what we end up to cancel polarization parallel to K mu. And what we're left with is, so if you think about it, there's one condition here, there's also one condition here. So out of 4 degrees of freedom, one condition, so you're left with 2. So it's just sum from 1 to 2 of epsilon mu s, and then what I call alpha s, alpha tilde s, let's say, of k e to the minus I k dot x plus complex conjugate. Okay. So this is the basis. This is the basis polarization vector. And this is some arbitrary Fourier coefficient. And because we have a massless particle, k squared is 0. Right? K squared, which means k alpha, this is 0. Okay. So this is where we were. But I just want to say a few more words about this. So what we realized was that k mu, epsilon mu s, in particular, is perpendicular to k. Is perpendicular to k, and also it cannot be proportional. It's not some number times k mu. Okay. So what does that mean? It means that, for example, and this we did the last time, if k mu is propagating in the third direction, then k mu downstairs will be k 1, 0, 0, minus 1. Then that basically means that epsilon s equals to 1 and 2, mu is either, for 1, it would just be 0, 1, 0, 0, and for 2, it would be 0, 0, 1, 0. Or some combination of this. Okay, and in fact, that's the Cartesian basis. That's the Cartesian basis. What I want to write down today is to show you, because I didn't have the formula with me. I just want to write down the helicity plus and minus 1. Yes, there we go. So instead of this, if you instead write down epsilon plus minus mu, it is defined to be 1 over root 2 of 0 minus plus 1 I 0. Then you find that, I guess I should put a transpose on all of these guys if you want to view your vectors as columns. Doesn't really matter a lot if you know what I mean. What you find is that these are actually the helicity plus or minus 1 polarizations. Okay. So this is of course assuming that k, the photon is propagating in the third direction. If it's not, then how do we do it, right? So then that's the other question. So in the situation where you need to deal with a more general case, how do you write it in a way that is consistent with what we have found, right? In other words, we want to find a way to project the polarizations only in the space that is left invariant under the middle group. That's the group theoretic way to talk about it. So how do I do that? So in fact, so let me just write this down. So the more general case, so this is for k going in the third direction. The general case is that you first define the projector. Pij, which I'm going to I'm going to just write down and explain what it means. It's going to be Kronecker ij minus k hat I, k hat j. Okay, and where k hat I is just the usual unit vector, so it will be ki, but divided by k, where k is the magnitude of the momentum. So what if you know a little bit of differential geometry, you would recognize that Pij is actually the induced metric in the space perpendicular to k vector, right? So choose an inertial frame, and then with the inertial frame, you can look at your momentum in space. And for a given momentum k, you can use this object to define the space that is perpendicular to k. And why that's the case is because we want to look at the polarization perpendicular to the momentum vector in space, right? So basically, you see the zero component is always going to be zero. So all you really need to think about is what is the space perpendicular to the k direction. In this case, the k direction is going in the third direction. K is going in the third direction. So it's easy to write down the two polarizations perpendicular to k. But if it is not so straightforward, if k is pointing in a general direction, then this is how you do it. And how do you check that? So you check the following. You check that Pij dotted into k, for example, is symmetric. So I just need to dot it into either I or j. Then, in fact, I'm just going to do it, okay, so then it will be ki Kronecker ij minus, let's do it for upper indices so that, okay, so that I don't have to worry about my signs. So k hat I, k hat j, so Kronecker dotted into k just gives you kj. Okay, and then k hat dotted into k is just basically the magnitude k times k hat j. But magnitude times the direction is just k, kj. And so this is in fact 0. So anything that is parallel to k dotted into p is 0. Okay? But let's say, suppose let's say I have q I is perpendicular to ki, meaning q dot k is 0. Okay? Then let's check that what happens when I dot q into p. Okay? And I claim that this will recover q itself. So let's do it. So it's Kronecker ij minus k hat I, k hat j, and then I dot into qj. But like I said already, k dotted into q is 0 by assumption. I'm assuming that q is perpendicular to k. So therefore, this will drop out, and I'll just automatically get back k, q, qi. So what have I shown? I've shown that anything perpendicular to k, when I project it with my projector, I get back itself. Anything parallel to k will be completely killed once I dotted into P. Okay? So that's what it means to be kind of an induced metric perpendicular to K. Because it will give you the same thing that if you are perpendicular to K, and it will give you 0 if you are parallel to K. All the components. So I.e. Pij takes any vector, say B, and throws away all components parallel to K upon projection. Okay. So how the heck is it going to do with what we're doing? So this is where this guy comes in. Okay. So instead of writing it in this way, I'm going to say, let me choose an inertial frame. Then because I've shown that when I cancel out the component parallel to K, and let me just remind you guys, so cancel out component parallel to K mu, and if you impose the Lorentz gauge, then you'll find these two conditions will let you find that A0 can always be set to 0. That's exactly what's happening here, if you remember. Then I need to only focus on the spatial components. And in that case, AI is now always perpendicular to K. But what does that mean? So remember that there is an AI, so I should say A tilde I is always perpendicular to K. Okay? But in Fourier space, if in Fourier space AI is perpendicular to K, that means that in position space, you have that AI is actually divergence free. Because remember, partial I has a relationship with Ki in that when you go to Fourier space, it's a minus I Ki. Okay, the minus sign depends on your convention, but it's definitely parallel to Ki. So if in Fourier space, it's perpendicular, which means K dotted into A tilde is 0. That means in position space, partial AI summed over I is 0. And that means what we need to do, if you forget, just remember this, right? So K dotted into these two guys is 0. And therefore, if you want to write this statement for general K, because this only works for K going in the third direction, what you can do is you can sum over all three components. You are in three-dimensional space, so you can sum over all the three basis vectors if you want. But what you can, so for example, you can use the Cartesian basis, epsilon s I. Okay, let me call it J for the moment. But then, it doesn't matter. So this can be any good basis for the three-dimensional space. Because I can then just write down Pij summed over J, and this projector will do the job for me. Okay, this projector will project out. It will project out automatically the components parallel to K. Okay. And then I can go ahead and say this is now alpha tilde S, again, e to the minus I k dot x. This dot product is the four-dimensional one, not the three-dimensional one. Even though I'm writing it for the spatial components, and this is still k mu x mu, and then plus complex conjugate. Okay. Yeah. Let me just put the curly bracket here. Okay. So that's how you do it in general. Okay. The free photon. This is the way to write down the free photon solution in the classical limit. Okay. Any questions for me? So again, what we've done is we've gotten rid of all the superfluous stuff, and we have recovered what we have learned from group theory, right? So let me write that down because it's an important insight that is worth reiterating. So this solution contains the two polarizing plus or minus one helicity. Let me just call it a classical photon solutions. And this is, remember, we expected this. From symmetry considerations. In fact, let me just remind you, that is the Lorentz Poincaré symmetry considerations, right? Meaning, we said that if you do your group theory right, you will discover that in 4 dimensions, massless particles associated with spin 1 really only have 2 helicities. Why? Because you look at the little group that leaves, if you fix your direction of propagation, Whitner showed that the representations of the full Poincaré group can be reduced to the study of the group that leaves the momentum invariant, which means that you're just studying the group that rotates the momentum in the perpendicular direction. This is also why this Pij shows up here, right? And that is just nothing but SO2, the rotation group in 2 dimensions. At least for finite dimensional discrete representations, you only need to care about SO2, right? That's the continuous spin that nobody cares about. But certainly we should care about the photons. And now what we're seeing is the explicit realization in terms of the solution of the Maxwell's equations that gives you a concrete representation of what we have expected from group theory. Okay? And so the next step is, in fact, to quantize this and see how the quantum particles come out of this. But that will take a little bit of time. We'll still need to do some Lagrangians and all these rules of quantization and so on. But even before that, I want to talk a bit about U1 symmetry, because actually, from the particle physics point of view, this is only one side of the story. So the symmetry from the space-time perspective is only one side of the story, right? The other side of the story is related to what is called U1 symmetry. So U1 symmetry is not a space-time symmetry, and particle physicists, whenever it's not a space-time symmetry, they call it an internal symmetry. So let's talk about that a little bit. Let's talk about that a little bit. Yeah, okay, so U1 symmetry and photons. So we'll discover this again, but now from a different perspective. So the way to do this is to consider quantum mechanics first. So in quantum mechanics, if you're working in the position representation, the wave function is a complex function of space and time. Okay? And so this is complex. And we know that if you multiply the wave function by a phase, theta psi t of x, this makes the phase makes no physical difference. Of course, mathematically, psi is not the same as psi times the phase. But physically, we would say that these correspond to the same physical state. And why is that so? Because only the square of the wave function gives you the probability, right? So because it's the square of psi that gives probability. In this case, if you're talking about the wave function, the psi square gives you the probability density of finding the system in a particular place in space. If you're talking about the wave function in momentum space, then it will give you the probability density of finding the particle in that momentum region, and so on. You can write it in any other basis, and it's the same interpretation. The square of the state evaluated in a particular basis will give you the probability density in that how should I say, the eigenvalue probability density. That's what I would say. Now, and because it's a square, the phase drops out, and you don't really care. Okay. The problem comes when you need to take derivatives of your wave function. Okay, so it's not really a problem, but it's a motivation, right? So the issue is, let me just say, the issue arises when taking derivatives. And if it is because really that's all to it. You're not really dealing with a space-time coordinate transformation. But the solution to this issue, which is to say how to restore covariance, is very similar. In the differential geometric solution, you add to it a Christoffel symbol, which transforms. This is not a tensor, but it's not a tensor in exactly the same way that this is not a tensor, or rather exactly the opposite way, so that they cancel out. The non-tensorial property of this will cancel the non-tensorial property of this, so that the whole thing may be defined as the covariant derivative of some vector, and this whole thing is a tensor. So this is not a tensor. Okay? But together they form a tensor because the two have non-covariant properties that cancel out. And likewise, we're going to do exactly the same thing here. So in field theory, instead of writing an inverted triangle, we call it d mu of psi. And how is it defined? It's defined through taking, starting with a partial derivative, and then introducing a potential. And you can guess why you need a potential, because this is a one-index object. Right? So you need another one-index object to exactly transform in the same way under space-time transformation. But usually we stick in a minus IE, and the way to remember this is that minus I partial is a Hermitian operator. And A itself is a real object. So to compensate for the fact that now you can think of this as I, you can think of this as I times, you can think of this as this, right? So I times partial is Hermitian, and I times this guy will cancel out the I, and then you have a real object. But I will, for the moment, I'll leave out the I outside, because convention tells you that. Maybe I'll put the ID so that you can see what I mean. Right? So this is a Hermitian operator, and then now you have a real object. Right? This is how you remember this. There must be an I here. And then let's do this. Okay? So now let's see what happens when I transform my let me actually start with 5 first, and then because I'm going to need to rescale it a bit later. So in fact, let me do the following. Just for convenience, I will actually stick in an E and then theta. Right? So we'll always have a non-zero charge. So it's okay to stick in an E, because theta for now is arbitrary anyway. So let's see what happens. Okay? So now we know this is going to be I, and then of course I will still have a derivative on this guy from that partial mu. Now I have I e theta e to the I e theta psi plus e to the I e theta partial mu psi. And then of course I need to remember this guy, which is minus I e a mu psi. Okay? And then what I'm going to do is I'm going to pull out my e to the I e theta, okay, and then I. And then what I have is I have partial mu, that's the second term over there, and then plus IE, and let's see what has happened. Okay, so let me put a minus, a mu from this term, and then let me gather that term, minus partial mu, there's an IE here, and now you see why I put the IE, because this IE came from this IE. so there's a common factor between the A term and the derivative of theta term. All acting upon psi. Okay? By the way, I started with the wave function for quantum mechanics, but in what we are trying to do, you can also think of this as the Dirac spinner, right? I haven't used any properties about psi except that it's a complex object, right? It wouldn't make sense to talk about multiplying a real object by a phase because it's real, right? I don't want, if I want it to be real, then I shouldn't be multiplying by a phase. But any complex object can be used in this argument. So it can be a wave function from quantum mechanics. It can be a scalar field, which is complex. Or the most important example is the Dirac spinner for the electron. Right? So this, in fact, you can think of it as the electron, the Dirac spinner for the electron. But here we are. We discover that this thing does not quite transform as you want, because this part is D. But I have this shift by this gradient. But this is where you remember that F mu nu, which is the antisymmetric combination derivative of A, if you remember, this is in fact invariant under A mu shifted by A mu plus some anything, basically. Okay. So what it means is that I can say that this is in fact covariant if I simultaneously shift psi by a phase and shift A by exactly plus partial mu theta. Okay? So let's write that down. So it's not covariant on its own, but if we simultaneously do the following, psi goes to e to the I e theta psi, where theta now depends on space-time. By the way, when I put x, I mean space-time. Right? When I put an arrow on it, it means space. And A mu is replaced with A mu plus partial mu theta. Then we discover that let me drop the I now, d mu psi would go to d mu of e to the I theta psi, and actually, let me just say, it will transform e to the I theta d mu psi. It will transform, so the covariant derivative of psi, in fact, is transforms covariantly under U1 transformations. Okay? And then there's one last thing that you will discover in your homework, which is that if you have done some differential geometry, you would remember that the commutator of covariant derivatives on the vector field is in fact the Riemann tensor contracted with the vector field. Right? So it's now an algebraic, even though these are derivatives, once you compute the commutator on V, you will discover it's now just one algebraic object contracted with V. So likewise, you can ask the question, what is the commutator of covariant derivatives using this definition, acting on, for example, a direct spinner or a scalar or whatever, anything that is allowed to transform under U1, you would discover, in fact, that this is e to the EI f mu nu psi. Okay, you will discover for yourself that there is a direct analogy, which is that the commutator will, in fact, give you the field strength. So even if you didn't know about it, even if you didn't know about this object, by taking the commutator, you will discover the field strength. So this is the way particle physicists would like to think about electromagnetism, which is to invoke a symmetry upon which they can then promote to a local one, right? So from a global U1 symmetry, they promote it to a local symmetry. Sometimes they call it gauge it. I mean, I don't like too much jargon myself. So, but this is often what they say. They gauge the symmetry. It just means you promote it from a local to from a global to a local symmetry, and as a result of that, you are compelled to add a gauge potential, which is an analog of the Christoffel symbol. The gauge potential is not gauge invariant, but when you write it in this form, the whole object, the whole derivative, will transform locally in a covariant way under your U1, in this case, U1 gauge group. And then you will discover the field strength, the gauge invariant field strength, by taking the commutator. And you can check directly, right? This guy is gauge invariant. And meaning is invariant under this gauge transformation. There's a lot of jargon which I don't like, but anyway, this is called the gauge transformation. I think I wrote it down the last time, but let me just remind you guys, this is called the gauge transformation. U1 in this case. The non-abelian case is more complicated. Like I said, hopefully in a few weeks I'll find time to revisit this problem. So, and then, of course, once you have an object A, then you want to give it dynamics, right? You want to give it dynamics, meaning it should have its own equations of motion, right? But where does the equations of motion come from? To preserve the symmetry of U1, you want to build an equation of motion out of this guy, which, of course, then will lead you to Maxwell's equations, right? At least that's an argument that you can make. Which means everything will now be motivated primarily through symmetries, right? You might ask, is it unique, right? From U1 symmetry alone, can you kind of uniquely pin down Maxwell's equations? And the answer is that at least at low energies, the answer is that in 4 dimensions that does appear to be the case. Okay, so that, but that argument is going to be, it's hard to make right now. So hopefully as we go along, we can get a flavor of this question as we go along. Or at least if we do a bit more QFT, then hopefully I'll have the chance to explain a bit more. But there is an analogous argument, right? Maybe unique is a bit strong, but essentially, if you ask the same question for gravity, you get a very similar answer. you ask the question, okay, what if I try to gauge Lorentz symmetry itself? And what people will tell you is that, oh, then you get gravity. At low energies, the unique, at least that's what the classical physicists will tell you, the unique four-dimensional massless spin-2 theory is nothing but general relativity, right? Just like they will tell you the unique low-energy massless spin-1 field theory is, in fact, just Maxwell's equations. Okay, and then you can make the same argument for gluons and so on. So that's why in particle physics, in field theory, symmetry is so important. Right? Once you know your symmetry, it fixes the type of field theories you can cook up. At least that's the assertion that people like to make. Yeah.
It seems that
Yeah.
we have assumed there's interaction between the gauge field and spinner because we need to simultaneously do the shift for psi and
Yeah.
So how to see the coupling between the gauge field and spinner?
That's the what do you mean? This is the complement, right? This is the whenever, in other words, whenever you see a covariant, whenever you want to take a derivative of a spinner, you want to introduce a gauge field if you want it to be charged under U1. That's basically the point. Otherwise, if you don't do that, then it will not transform covariantly under U1 symmetry.
Could we say that the non-vanished principal symbol is due to the actual geometry is sphere?
Yeah, so like I said, I prefer, at least my own understanding is that I prefer not to push the analogy too far. Because, A mu is a separate degree of freedom, right? It's not really part of space-time. When you put it in, it's not really part of space-time. It's an analogy. So let me emphasize that it's an analogy, not really the exact. It's not exactly the same thing, right? Because it's an extra thing living in space-time, and furthermore, the symmetry we're talking about here is a U1 symmetry, which again is not a space-time symmetry. It's a symmetry that I impose on my spinner, essentially, right? I want my electron field. This is my electron field, for example. I want it to transform covariantly under U1 transformations, right? Like that. I want it to transform like that, and I want it to transform like that even when theta depends on space and time, which means that even the derivative I want it to transform like that. So then I realized that the way to make it work is to add this thing, this A mu, to my derivative to make it work. Otherwise, the partial derivative itself will not preserve that U1 symmetry. Right? Yeah. So it's a motivation. Right? Don't take the, in particular, don't take the. That's my take on it. Right? Don't take the analogy between space-time and A mu too literally. The Christoffel symbol too literally. Because one is really just space-time. The other one, you're adding stuff to it. Yeah, and then it gets even more complicated when you do gauge non-abelian gauge theory. Then you have a cover index and so on. Yeah.
I have
Yeah.
a question. So what is physical meaning of simultaneously transform using the phi and
Yeah, it's a little bit abstract. So all I can say at this point is that it's a symmetry that I have to impose on all the electrically charged fermions in nature. That's what I can say. But the consequence of that is that it is realized in nature, right? Like I said, all the electrically charged, I should say that because that's an important point, right? So in fact, this whole discussion applies to all electrically charged matter in the universe, in our universe, right, in our world. But in particular, the electrons and its antiparticle, the muons, the taus, the quarks are also charged. The only things that are not charged are the neutrinos, right? Everything else is charged under U1. And so all the quark fields, all the neutrino, the electron fields, muon fields, tau fields, all would have to transform like that. And so the field theorists would like to say, no, let's start from the symmetry. And then from that, you will discover charged matter in the universe. Right? So they're trying to say that symmetry comes first. But it is true that in this case, it's not very intuitive, right? And I think that's probably what's motivating your question. Right? It's not very, it's not very intuitive. And that's why I start with quantum mechanics, right? At least there you have some sense that the phase doesn't matter because you square it and the phase disappears. But that's a local, that's a global. We talk about that in the context of a global symmetry, right? And now you try to promote it to a local symmetry, meaning let the phase depend on space and time, and see what happens, right? And then you discover you need a mu, and then you have electromagnetism, right? So it is a bit more abstract. Internal symmetries are a bit more abstract, but it is a very what I can say is that it's a very fruitful way to think about symmetries, because, like I said, even gravity can be thought of it in this way. So it's a little bit more technical, right, and less intuitive. But like I said, ultimately, the reason why we do the physics that we do is because nature somehow is like that. Yeah. Okay, let's take a 10-minute break, and then we'll come back. And once you do that, then I claim that the Euler-Lagrange equations are equivalent to the following things. Firstly, Pi dot, so this is Euler-Lagrange, and then here we have Hamilton's equations. Sorry, you guys have to read it upside down, but so it looks like this. Pi dot is equals to, this is acceleration, this is NA, right? It must be minus dH dq, okay? And then you would also have Q dot equals to plus dH. So let me make my notation consistent. dPi. Okay. So for example, let's do the simplest example. Okay. So the simplest example is in classical mechanics. The Lagrangian is often just half mv squared. So it's just kinetic energy minus potential energy. Okay. And then dl q dot is just in fact momentum, which is nq dot I, which we define as pi. Okay, so this guy, so that's what the Lagrangian itself is just P squared over 2m minus V of Q, right? In other words, we use, like I said, you use this guy to invert Q dot for P, and then you plug it back into the Lagrangian, and what you discover is that when you calculate what the Hamiltonian is, you discover that you get Pi Q dot I minus L, but Q dot is just P over M, and what you discover is that you get basically P squared over 2M plus V of Q. In other words, it's just total energy, where Hamiltonian is most often just nothing but just kinetic energy plus potential energy, and the Lagrangian is kinetic energy minus potential energy. This is the most common example that you will discover, that you will play with when you take a classical mechanics course. So this is a very quick review of something that I hope you guys have seen. Have you guys seen this before? Okay, very good. Very good. So now we're going to play the same game, but for field theory. Okay, and so that would be important for quantum field theory. The classical version will end up being very important for the quantum version as well. So when we talk about field theory, so let's start with classical field theory. I should first say why the action principle, why the variational principle is important. And the reason is because the Lagrangian allows us to capture symmetry principles much more succinctly, right? Symmetry properties are much more readily. In fact, the punchline is the following. If you want your equations of motion to transform covariantly under some symmetry transformation, then the way to do it is to in fact cook up the right Lagrangian that is invariant under that symmetry group. In particular, so L, so this is the punchline. So if L is invariant under some symmetry group, some symmetry transformation, then the resulting equations of motion, EON means equations of motion, will transform covariantly under the same transformations. Okay. So invariance is much easier to check than covariance, because covariance always can be complicated. You have all these indices and whatever. You need to make sure that but invariance just means that the thing remains the same. Okay, so if something remains the same, it's much easier to check than if it transforms in some, non-trivial way. Okay, so that's the point of it. That's why Lagrangians, at the classical level, this is why Lagrangians are so useful, right? It just captures for you in a very succinct way the symmetry properties of your field theory. You look at it, it's invariant, then you know, this guy has this symmetry, right? Of course, sometimes it can be a little bit subtle as well, but for the most part, for all the things that we're going to talk about, you will see it's going to be very clear what the symmetry principles are. Okay, so but we'll build this up bit by bit, just like we did for the equations of motion, right? So the first thing to do is to, in fact, recover the Klein-Gordon equation, right? And so, and along the way we'll discover the realization of this statement for Lorentz symmetry. So, for example, if you want your theory, if you want the field theory, if the field theory is relativistic, you want to demand that the Lagrangian is Lorentz invariant. Okay. So for example, the Klein-Gordon. Let's cook up the Klein-Gordon Lagrangian. By the way, I should really call it Lagrangian density because we're doing field theory. So fields are defined everywhere in space and time, right? So the L is no longer a position as a function of time, but it's not a function. It's not a function of positions, which in turn are functions of time, but rather they're functions of fields. So I should really call this the Lagrangian density, but it's too many words, so I'm just going to call it Lagrangian. But coming back to what we're trying to do, if you want to cook up a Lagrangian for Klein-Gordon, you can actually guess it quite easily because it needs to be invariant. And if you remember the classical mechanics discussion that we had, where usually we expect the Lagrangian to be kinetic energy minus potential energy. So basically, you can guess that it has to look something like this. So this thing is something like kinetic energy. In particular, there is a time derivative here. This is phi dot squared minus 1/2 grad phi dotted into grad phi, right? This point. And then minus a quadratic potential that corresponds to the mass term. So this guy, you can think of it as a parabola in field space, and that's like the potential energy. Okay. So we'll see how it gives you the Klein-Gordon equation in a bit, but let's do it a bit more generally. So. What I do want to point out is that I hope it's clear by now that when the two Lorentz indices contracted to each other, it should be immediately clear that this is Lorentz invariant, right? This is certainly Lorentz invariant because it's a scalar. But having one index down, one index up, you know that this guy will transform in an opposite way from this guy under Lorentz transformation. So L is a Lorentz scalar. Okay. But let's try to do this analysis more generally. So let me just say more generally. Let's let our action be integral. We'll do mostly 4 dimensions, but actually it doesn't matter what most of this discussion doesn't matter what dimensions we're in, but I will assume that we're in flat space that does occur in, for example, general relativity, right? So this is for people who know some GR. So in fact, it turns out that GR has this problem, and it ends up being that you have to add an additional boundary term on the boundary to make sure that you cancel this the term that you get from integrating by parts. Right? So it's not. I'm not saying something that is just some esoteric technical point, but it actually shows up in gravity. Okay? But for our purposes, thankfully, we don't have to worry about this problem. So let me just mention it, but from now on, I'm going to assume that this can always be done, and I'll just vary the action and write down the Euler-Lagrange equations, right? So in fact, let me write that down. So in fact, because this term is 0, and I want delta S to be 0, then what you see is that the Euler-Lagrange equations for field theories, in fact, now looks like the following. You have dl d phi equals to d alpha, and then dl d alpha phi. Okay? And now, we have an example over there, the Klein-Gordon equation. The Klein-Gordon Lagrangian. And that's in fact seen explicitly that the Euler-Lagrange equations would give us what we expect, namely the Klein-Gordon equation. Okay, so let's apply it to Klein-Gordon. So if L, okay, let's just do it. So dl d alpha phi, what is that? So let's do mu, okay? So this guy means you take a derivative with respect to the derivative of phi, holding phi fixed. So I don't have to worry about this. All I have to do is I have to worry about what it means to differentiate. Let me write it down as eta alpha beta, partial alpha phi, partial beta phi. Right? That's all I need to worry about because this doesn't have derivatives. So what it means is basically I just treat these guys as a coordinate, and I just differentiate as though I'm doing ordinary calculus. So this is now 1/2 eta alpha beta, and this is alpha, that's mu, so I will have alpha mu, that's the derivative of alpha, d alpha phi, d mu, right, is just Kronecker alpha mu, okay? And then d beta phi plus 1/2 eta alpha beta, partial alpha phi, and then Kronecker beta mu. Okay, just a product rule. But altogether, once you get used to it, you see what's going to happen is just that it's going to give you eta, it's just going to give you partial mu phi. Mu phi because this guy will give you eta beta mu, and then eta beta mu will raise this index to mu. Same thing here, this will give you eta mu beta, alpha mu, and then again, these two guys will give you that, and then this will raise this index to mu, and the 1/2 will give you 1. Okay, and so then if you write down all the branch, starting from right hand side, partial mu dl d partial mu phi, that in fact we just discovered this is nothing but partial mu phi upstairs. This is now partial mu downstairs. This will be upstairs. And as I promised, you get a Lorentz covariant, well, it's a scalar equation. So it's again Lorentz invariant wave operator acting on phi, right? So it is very important that this is upstairs because this is downstairs. And then the other part is this guy. So d L d phi, that's easier to do because all I have to do is just differentiate this guy, treating this as like an ordinary variable, right? So there's a phi squared, so you get minus n squared phi. And so when you combine them together, dl d phi minus dl d phi equals to 0. When you combine them together, this gives you what? This guy is, remember, partial squared phi. This guy is minus minus or plus n squared phi. And of course, this is nothing but the Klein-Gordon equation. Okay? So, we have done this by explicit calculation, right? But next time, we will try to study this more explicitly, and we'll see that from the structure of the Euler-Lagrange equations, you will discover that from here, we can discover that what I said earlier, which is that invariance implies covariance. And you can kind of see it because L is unchanged under whatever symmetry transformations I want to do. It's this guy and this guy that will transform. Okay, and in particular, the way we write partial alpha would also guarantee that as long as these guys are scalars, this whole thing would also be a scalar. Right? So it's easy to see for the space-time symmetry. But there will be other internal symmetries that we will do. But the structure of the Euler-Lagrange equations will remain the same. And because of that, we'll see explicitly next time that invariance of the Lagrangian implies that the Euler-Lagrange equations, which are the equations of motion, those guys would transform covariantly under whatever symmetry transformations that you care about. Okay? And so that's why the Lagrangian formulation is so important. Okay? Any questions for me? So quiet.
Actually, I have a question. So,
Yes.
because when I read Laskin,
Yeah.
you say that it's a transformation that leave your Lagrangian invariant up to a certain
Right. I should really say that. Yeah. We'll talk about that in a little bit. When I talk about the Noether's theorem, yes. So I should be a bit more careful. So invariance up to a total derivative. Yeah.
So,
Yes.
so first, Yi-Zen first said that we found the Lagrangian to describe K-Gordon equation.
That's the one.
And
Yeah.
so as we found the Lagrangian, next day we will use it to get some observable transformers to do.
I don't understand. What do you mean by observable transformation?
So what kind of observable transform we write?
Observable transformation? I'm not sure what you mean. Do you understand what I'm saying here? So what I'm saying is that I haven't shown it explicitly, but I am saying that if your Lagrangian is invariant up to a surface term, up to a total derivative of under whatever transformation that you care about, maybe Lagrange transformation, or we'll do U1 transformations. Once you guarantee that your Lagrangian remains the same, then the equations of motion would be covariant. That's what I'm trying to say. Okay.
When we write down the
Yeah.
Lagrangian equation, we have assumed the conjugate momentum vanish at the spatial boundary. And what seconds?
You can also do that, yeah. So you can either assume that this vanishes or this vanishes. Yeah. What I'm assuming is that this guy vanishes. Because that's the variation, right? That's the variation. But I'm not assuming the way I'm doing it, I'm not assuming that the conjugate momentum vanishes. I'm assuming that the variation of the field is vanishing because I've fixed the fields at the boundaries. Yeah. You can also formulate it in that way, that demanding that the conjugate momentum vanishes, but we may have to adjust. We may have to adjust this. You may have to adjust your boundary terms appropriately. Yeah. You see what I'm saying, right? Because this may not vanish, right? This is your P, but it may not vanish on the boundary unless you find a way to make it so. Right. But this vanishes because delta phi vanishes because sorry, I erased it already. But I've demanded that the initial and the final fields are specified. Right.
If we consider the field on the sphere of a cylindric, then we don't worry about the boundary term.
That is correct. That's correct. Then there will be no boundary terms to speak of in the first place. That's right. If you're doing Euclidean field theory, for example, right? I don't know what it means to do a sphere in space-time. You don't want to have closed time-like curves, right? You can have a sphere, but then you end up having a closed time-like curve, which is not very good for space-time. But if you're just doing Euclidean field theory, then you're right. That on a sphere, then there's no boundary terms to talk about. Then it's okay. Yeah.
Yeah. Yeah, I have a question.
Yes.
So, if we think about classical mechanics, and if we try to remove the mass term from the Lagrangian
The what? The mass term.
Yeah, I mean, and so here the first derivative of time of phi is the
This one?
Is the kinematic energy.
Yeah,
The
yeah.
other term is the potential energy.
Yeah, so you can think of this as kinetic energy.
Yeah.
This is like gradient energy, right? So because this is saying that if there's a non-trivial gradient in space, that actually contributes to energy. You can think of it as, because this is negative definite with a minus sign, right? So you can think of it as part of, I guess you can think of it as part of potential energy, but it comes from the fact that there's a gradient in space. I don't know if that's what you're asking, but.
Yeah, what I mean is that.
Oh, you're asking about mass. If you drop the mass.
Yeah. Yeah, so if we drop the mass, we have the classical wave equation.
That's right. That's exactly right. If I don't have the mass, then where was it? Yeah, then I just have the wave equation. That's exactly right.
Yeah, and so can we think of that if we add the mass term into the Lagrangian of the wave, we can it means that we introduce a new potential into.
That's exactly right. Yep. Yeah. Mass is like a potential. In fact, in inflationary cosmology, that's exactly what people do. The simplest inflationary cosmology is actually just this guy here. You use the mass term to inflate the universe.
Okay.
Yeah, that's
Yeah.
exactly right.
Yeah.
Yeah,
Yeah, so that's what I want to ask.
yeah,
So,
yeah. Good. And we'll do this also in Fourier space in a little bit, okay? Because I haven't talked about this as well, but since you mentioned this, when you go to Fourier space, you'll discover that in Fourier space, this interpretation becomes even clearer in the sense that it becomes, in Fourier space, the Lagrangian for the simple harmonic oscillator. So simple harmonic oscillator looks like that, right? And the Lagrangian is 1/2 q dot squared minus omega squared q squared. Right? Let's just do it in one dimension. So kinetic energy minus potential energy, but with the omega squared. So what we'll discover is that when you go to Fourier space, then your Klein-Gordon Lagrangian would look something like this. You will have phi dot squared, okay, and then minus energy squared, as 1/2, and then phi squared. And what is energy squared? It corresponds to this omega squared. And the energy here is actually your spatial momentum squared plus m squared. Right, so E is just the usual energy. But now you see that the analogy with the simple harmonic oscillator is very clear. You see? And that in fact will be the basis of our quantization. I think you've seen it once already, but we'll see it very soon, I hope. Right? But yeah, that's the next step. We'll talk about symmetries, and then we'll return to this question of what the solutions are, but from the viewpoint of comparing the quantum to the harmonic oscillator, because that's the stepping stone to quantization. Like I said before, quantum field theory, at least perturbative quantum field theory, is all about excitations of the field about the vacuum. What are the excitations? They are actually all simple harmonic oscillators. It's just that you have a simple harmonic oscillator for every k mode, and each k mode can have, for bosons, you can have infinite number of particles for each k mode. For fermions, you can only have one. But that's actually going to be the basis of quantization. Yeah, it's just basically simple harmonic oscillators.
And
Yeah.
if the Klein-Gordon is kind of similar to the wave equation, can you think of that the Klein-Gordon equation describes the motion of a wave that travel at the speed of light?
It's a wave in k-space, yeah. The harmonic oscillator, in some sense, is just a wave in k-space, yeah. Yeah.
And
It
it
is.
can travel at the speed of light.
Mhm.
Correct?
Yeah, that's exactly what the plane wave does, right? Remember that the e to the I k dot x, if you write it in, let's just let the k go in the third direction. This is just e to the minus I k t plus or minus kx, right? And then you just factor it out, e to the minus k t plus or minus x. And that's just a wave that is going either plus or minus x direction. That's exactly right. Yeah. Yeah. So there's a relationship between all of them, right? The wave, the simple harmonic oscillator, and particles. All of these things are going to be related to each other. Yeah. Good. See you guys on Thursday, Friday.